Hello, guys. Welcome back to MedZone African Motives. We are still on our Mechanotechnics N4 that is working on the bearings as a request from the membership section that we need to cover up this section. Actually, yeah, guys, there are a lot of things that we need to cover up, but we shall see with time. Without wasting time, guys, we are going to look into the bearings, which is actually one of the important part of our modules. That is module number 8 of our syllabus as we consider our mechanotechnics N4. So it is the basics that when we are dealing with bearings, guys, these are actually, like we are saying, bearings are machine elements that are used to reduce friction between moving parts and to enhance the speed and efficiency of a system. So that is the basics that we can actually say about our bearings that are machine elements. All right, so these are machine elements that are used to reduce. So they must reduce friction. They must reduce friction, which is found between moving parts. All right. Found. Did I put the word that are used to reduce friction between what? Between moving parts. All right. Between moving parts. And I also added that they must enhance and to enhance. That must enhance the speed and what? Efficiency. Speed and efficiency, which is of a system. So this is the basics that we are referring to. Bearings are simply machine elements that are used to reduce friction between moving parts and to enhance the speed and efficiency of what? Of a system. So as part of your syllabus, you are required to know the loads acting on bearings. What exactly will be when we are referring to the loads that are acting on bearings? So I'm going to refer and add information to what we have referring to your textbooks. I'm going to add some of the information, but as a basic introduction from what we just had, we can simply refer here as bearings are devices that are used to support shafts. They are used to support what? To support shafts. As we are referring to our bearings, they keep the shaft stable and allow it to rotate without friction. They keep they keep the shaft stable. Major part there supposed to be stable and allowed it to rotate without friction. So the motion is limited by bearings, which only allows for linear and rotational motion about the axis. So we are saying we can have the condition of our bearings there. That is when we refer to the motion, the movement is limited by bearings. All right. So this, if we consider in terms of the shaft, we can see that the shaft can rotate or shift. It can rotate or shift axially in the bearing. So here it's gonna be depending. Let's put it this way. Depending must be depending on bearing type. All right, so that's depending on what? On bearing type. Depending on bearing type. So what am I trying to say here? Some bearings allow limited, all right, because some bearings here, all right, some bearings allow limited, all right, they allow limited axial movement. Remember, talking about the axial here. So they allow limited axial movement. For an example, we consider the deep groove ball bearings. All right, let's consider that for an example. The deep groove, all right, ball bearings. So that part, they do allow, they allow limited axial movement, while others restrict it. These ones, they allow limited, while others, they do limit. While others, they do restrict at all. While others restrict it. All right. So that's when we talk about the rotation, the shaft can rotate or shift axially in the bearing. That's depending on the bearing type. All right, depending on the bearing type. So we are going to dwell much on the bearing type later on. So as for the basics, this is what you're going to need. And also bearings are made to take pure radial loads where there is rotation only. Talking about rotation only. Pure axial loads or combination of both. So you can have a pure radial, we can have a pure axial on its own, but we can have also a condition where these are taken both at the same time, meaning to say the radial load and the axial load at the same time. So what exactly are we referring to there? Different bearing types are designed for different load conditions. In actual sense, different bearing types. Different bearing types are designed for what? For different load condition. For different load conditions. We must consider that, which we are referring to as the radial, where there is rotation only. Then we have got the axial loads. Which type are we talking about there? The axial load can also be referred to as the thrust. All right, so we can have this one as the thrust. So let's just also put here as the thrust. That is the force acting along the shaft, which is parallel. All right, so this one is force acting along, it is acting along the shaft, which is actually a condition of what? A parallel. They are in parallel. So it can be a push or pull direction. It can be a push or a pull direction that we are given there. So the basics, all right, I have something here. All right, if we consider here, the radial load, all right, is the one that we started with as part of the rotation. Then we talked of the axial load. These are two that are being applied. The loads applied on our bearings. So we've got the first one, which is the radial. So we said for the radial load, It is just a condition of what? Rotation only, which is a force perpendicular to the shaft. So if we consider, in this case, the radial load will be perpendicular to the shaft, okay? We'll be having the part of your shaft, so this one will be perpendicular at what? At 90 degrees. Whereas the axial load is parallel. The shaft is here and is going along with the shaft. So it is a parallel. All right, so here we are saying this one parallel, and this one is what? Perpendicular. Perpendicular. Okay, so that's the major concept that we are having on that part. So we're not going to add much, as you can see it on the diagram. So these are the loads applied on our bearings: radial, perpendicular, axial, parallel. So when we say axially, like axially, guys, the pronunciation is in your hands. All right, so that's around, simply around its own axis. Around its own axis. So that is what you must consider as the loads applied on what? On bearings. Then where FA, if we talk of FA, that is the acceleration force between the tire and the surface in the driving what? In the driving condition or the driving direction. So we are going to notice that all these can be put together when we consider a bearing. The main elements of a bearing, we are going to have the outer ring, we also have the inner ring, the ball, and the cage. So those are the main elements that you must consider whenever we see a bearing. So in a simplified version, we can put it this way. So we have got the outer ring. All right. Then we have got the inner ring. All right. Then we have got the balls in that case. All right. So we've got the balls that are here. So this is the illustration that is presented in an easier approach. We can now see this way. So like I said, we have got what? The outer. So this is our outer ring. All right. Then we have got the inner ring, this one. So here, that's our the inner ring. All right. Then we have got the cage. All right. So the cage is here. So this is our cage. And we have got the part representing what? The ball. So these are balls. So here we can just call it ball, as we are referring to one. So that is the case of what we are seeing here. This is the case of what we are seeing there. So these are the main elements of what? Of a bearing, which are the inner ring that the shaft fits into, the outer ring that is fixed to support or housing and rolling elements between the two rings that allow the inner ring to rotate. So let me just add on this information. Okay, we can just add, guys, as you are reading this information, just go through each and every part. So here you can just add, just need to add one or two. So as we consider the outer ring is fixed to support, it is fixed to a support, or a housing. So this one is fixed. It is fixed to a support, or housing. Okay. Then the inner ring, which is mounted onto the shaft. It is mounted onto the shaft. It rotates together with the shaft and provides a raceway for the bows. This one. It rotates, all right, together. It rotates together with the shaft. It rotates together with the shaft and provide raceway for the bows. So this is the case that you can put for the inner ring. It is mounted onto the shaft. So it rotates together with the shaft. Then the bows, here, as we consider the bows, all right, they are found between the inner ring and outer ring. So there's nothing much that we can just say here. Just found between the outer and inner ring. All right, then we have got, all right, the main case. Okay, so you let me remove this so that we can put the main case. The main case, they are to reduce friction and allowing smooth rotation. They also carry the load. They also carry the load. That is the radial. It can be axial or it can be both. These balls that we are talking about, they are also referred to as the rolling elements, right? So the balls are also called rolling elements. These are our rolling elements. So like I said, they are found between the inner and outer rings, which is fine. And as a major case, they reduce what? Friction. And allow smooth rotation. And allows smooth rotation. That's a case of the balls, our rolling elements. They also carry the load, all right? So they also carry the load. So that's another aspect that you must put into consideration. Then the ball, the cage, which is the last part that we must consider here, which is the cage. So here I just wrote it this side, no problem. So let's consider the cage, which is also referred to as the separator. So the cage is also referred to as the separator. It keeps the bows evenly spaced and prevents them from rubbing against each other. All right. So here it's a major part. Very, very important. Keeps the bows, all right, keeps the bows evenly spread. All right, evenly spread and prevents them from what? From rubbing against each other. From rubbing against each other. So that's a major aspect that we must consider about the cage, which is our separator. It also guides the bows and maintains smooth motion. Another aspect, very, very important. It also guides the bows, all right? It guides them and maintains smooth motion. Smooth motion. So that's for the cage, the separator. If we are given these main elements of the bearing, of a bearing, we must be able to tell the function of each also. as you know them, just as an individual, try to understand the basic functions. All right. So without wasting time, guys, just go through, like I say, the sources that you're having, depending on the textbook that you're working with. We're gonna quickly rush to the types of loads acting on shafts. As we stated before, there are different loads on bearings, all right? As we referred the axial load, which will be parallel to the shaft, and the radial, which is perpendicular to the shaft, okay, which is fine. But in most cases, or in the revision that you're going to need, we want to put them differently in terms of these loads that are on a shaft. So we have got the basic names, actually names that we are going to use, which are the static loads on shafts, and we also have the dynamic loads on shafts. So we must understand them in that way. Static loads, what exactly are we referring to? A static load does not change in magnitude or direction, does not. It gradually increases to a steady value. For an example, the dead weight of machine elements. So this one does not change in magnitude or size, which is cannot be affected in terms of its magnitude or size or the direction. So when the shaft has various components such as pulleys, gears, they place a static load on the bearings. The reactions. The weight of these components, if significant, must be considered. In components that use belts, the installation tension also places a load on the bearings. So you'll find out that the weight of the shaft, if large, must be taken into account. The weight of the shaft, if large. So whenever they give you the mass of the shaft, then they will give you the mass of the gear. There you must consider to say you must calculate the weight. The weight of the shaft must be considered, which is the force, where you have to take it as a resultant from, we're going to talk about that one later on, from the normal force and what? And the total weight, which is the total weight considered from what? From the weight of the shaft and also the weight of what? Of the gear. So they are saying if that weight of the shaft is large, if it is large, we must take it into account on our simplification. All right. So always the weight always acts vertically downwards. All right. When we consider the weight, it acts vertically downwards. Remember, due to our force of what? Due to the gravitational acceleration. So when we have got a certain, let's just consider even a block. Let's say we've got a block that is placed here. When we consider the weight of the block, we take the one that is acting downwards. But here we are saying the belt drive, which is shown acting vertically upwards, can be placed so that the installation forces act in different directions. It can happen like that some cases you are given a condition where a certain force is going up, which is when it is going up, when you consider the condition of the force that it can go up, it is the normal force. It depends with the diagram. The normal force also is supposed to be going down, remember, from our N3 engineering science. But when you are given a condition where it is going up, then you must calculate the total force, which is the force of the shaft from the resultant. You have to consider, all right, or both of them, they are going down, so I must add. One is going up, one is going down, so I must subtract because they're opposite. You're now back to your engineering science, this and that. All right, so this is the aspect that we're going to look into later on, working with what? With our calculations. But as we consider this diagram, here we have got the weight of the shaft, right? The part of the shaft. So you're going to have the weight of the shaft, which is going down, the weight of the gear, which is also going down. These are reactions on the left side. Then we've got the other one on the right side, where we have to consider, remember your moments whenever there is forces going down and other forces going up. So we can use sum of forces going up is equal to the sum of forces going down on those calculations using moments, this and that. So in most cases, we are going to see the presentation of our spur gears later on, which are the ones that we're going to talk about, which will be centrally attached, so that that's the most case that you're going to have in your syllabus, where they are centrally attached. And when they are centrally attached, these reactions will be equal on the left and the one on the right hand side. So we're going to talk about that one later on. But for now, here let's consider where we have got the weight of the pulley going down again. Then we have got the installation tension by the belt, which is going up. So you must consider tension, weight, force. As long these are acting on a body, you must consider them. They give you in terms of the tension, in terms of the weight, in terms of the force. This is what we need. So we must have the resultant from that. So we consider the directions. What is going up, take it as a positive. What is going down, take it as a negative. Not actually to say we take it as a negative, but in terms of that, just the understanding. But when we refer to these forces, guys, the weight, the tension, whether the diagram is another presentation that you are given, you've got your shaft here, then there are bearings which are being attached at the end of the shaft. Then we have got the load here. The issue is on the diagram that you be given, guys. They can give you, we are used that the reactions which are our supports, they're supposed to be facing up. But if they give you another condition where the reactions are facing down, you work with that, guys. You must work with that. You must consider that. So we have got the reaction on the left and the one on the right. Normally, this is what we are used to. So these are the forces that are going up. So you combine everything that is going up. And where we have got our load, you can have this one as the gear wheel, whatever that you're given, which is your load. It must be going down, facing down. But they can give you this going up. And these reactions are the ones that are going down. You work with what? the diagram the way that you're given. You do not uh, fight against the question, guys. All right. As I always say, you answer the question the way that you're given, but you have your own understanding. Say, okay, this was supposed to be like this. That is not going to change how we are going to answer our questions later on. You just use it as it is. And also the other part, it will be on the dynamic loads, which are on the shafts. A dynamic load this time changes in magnitude and or the direction changes. Direction changes with respect to what? With respect to time. So an example that we can give there is of a load acting on the connecting rod of an internal combustion engine. The instant that the shaft starts transmitting torque, extra forces on the bearings come into play. Then we have the weight of the members on the shaft remains in the same and acts vertically what? Downwards, the weight. The weight of the members of the shaft remains the same and acts vertically down. Take note the weight. The weight, we talked about it, guys, that it is acting what? Vertically downwards. It is the Fn, which is our normal force, which can be given otherwise. But as for the weight, always downwards, okay? So that's what you're going to have in belt drives. The installation tension, which is T naught, when no motion occurs, falls away. It is replaced by tight side tension, which is T1, and the slack side tension, which is what? T2. Also, another part is you must also revise your belt drives, guys. As you are working with this topic, you must have the basics of your belt drives and also gear drives. You must have the basics of those topics, all right? So that it's not gonna be much complicated to understand these terms, but just go through these terms. And another important aspect is when we consider the loads that are on parallel shaft, all right? Sorry for that, guys. The loads that are on parallel shaft. Loads on parallel shaft gears and cross shaft gears. So given different loads that can be connected or be given on a certain shaft, can have parallel, can have cross shaft. So the loads on bearings and on the shaft carrying them originate from the meshing of the gears under motion. The meshing of the what? Of the gears, which is the connection where the teeth of the two gears are engaged. That is the meshing part, where they are engaged with each other so that one drives the other. One is supposed to drive the other. So we are going to see that for shafts that are parallel to one another, spur and helical gears are used. For shafts parallel to one another, we are going to focus with what? Spur and what? Helical gears. Those are the ones that we must put into consideration. Helical gears are stronger and quieter than spur gears with this straight teeth. They are very strong and quieter in terms of the noise. They are very quiet. But the disadvantage is that they create side thrust. This needs bearings to counteract it. We need bearings now to counteract that. That's being expensive at the end of the day. So to reduce the amount of side thrust, double helical gears can be used. And by doubling now, that makes this to be expensive. These gears are expensive. So that is what we are given on Fig 8.5, where we have got the spur gears, parallel connection. They are parallel to each other. We can have single helical. We can have a double helical, which is now to reduce that amount of side thrust. Remember, we said we're going to need what? A double helical gear. So those are the presentations basically that you are going to need. Then the forces on what? On spur gears. Remember, when we just talk about the spur gear, guys, we talk about a condition where these two are what? In parallel. We must consider a parallel connection there. So here I am going to just illustrate the basics, guys, that we have on this presentation here. The simplest, most common gear system uses external spur gears. These are cylindrical gears with a straight teeth parallel to the axis. They are used to transmit rotary motion between parallel shafts, which rotate in opposite what? Directions. So this is what we are given. And on the forces that are on the spur gears, what we can conclude from this, guys, is that one, as we said, the shafts are in parallel, the loads on parallel shaft gears. So the shafts are parallel. So that is considering these two gears in mesh. The one is going to drive another from the basics of our gear drives, guys. I'm not gonna dwell much. So the driver, which is the input driving the driven gear there, which is our output, it has the less number of teeth, which is our driver here. There's less number of teeth compared to the what? Less number of teeth compared to the driven. So you can see that, okay, this one that has got lesser number of teeth, that is our driver, which is also referred to as what? As the pinion. And the driven with more number of teeth, which is our gear or the gear wheel. From our information on the diagram there, we can see that there is an angle of 20 degrees. Then we wonder what is happening there. It is that the normal force, take note there, the normal force flows in the direction of rotation of the driven gear, through the line of action. And that is 20 degrees for metric gears. So that is why we are having this 20 degrees. It flows in the direction of what? Of rotation. And the angle in between must be what? 20 degrees. So we can consider having our normal force, the radial force, and also the tangential force. At 90 degrees, meaning to say we can use our trigonometrical ratios, guys, to find, remember the issue of the vertical component. So it's gonna having the sign of what? The sign of theta. If it is horizontal component, is gonna use what? The cos of the angle theta, which is what? 20 degrees. And that is identical to this side. It is one and the same thing. One and the same. So simplified drawing is the one that we are seeing on this side. With the two, the driver and the driven in mesh. This is what you're simply going to need, guys. Do not consider much there. You are back to your trigonometrical ratios, so you can find the vertical component, horizontal component. That's it. That's it. So we're going to look into the calculations, but let's just save these ones in short. So F normal, we can just write it as Fn in short. So that's simply our normal force. And that one is found in newtons, all right? Then we have got the radial. So you can just, that we have that one as Fr, which is our radial force. Also, it is found in what? In newtons. And we also have the tangential force, which is, we can just write it as Ft from the tangent concept, tangential force. Also in what? In newtons. So the other information, revise the gear drives. Like I said, the information on your calculations there, the pitch center diameters, the module concept, that can be best if you consider those things, because we are going to need those calculations again, because we still have what? The gear concept, driver, and what? And the driven. We still have that concept. So meaning to say, we must consider it. All right. So from that concept, this is what I was trying to explain, that the normal force follows the direction of rotation of the driver. All right. I think I was saying driven. Okay. That's the driver gear through the line of rotation, 20 degrees for metric gears, which is the one that we are using there. Then the line of action is also called the pressure angle. The normal force acts on the shaft of the driven gear. The shaft of the driver gear is acted on by the reaction of this normal force. It acts in the opposite direction. The shaft of the driver gear is acted on by the reaction of this normal force. The normal force is found by calculating it from transmitted torque. Yes, there are formulas. Like I said, we're going to list those formulas, okay? We're going to see where the torque is there to calculate the normal force. Then the radial force and the tangential force are components of the normal force, meaning to say we can have them from the normal force as long you've got the normal force, or maybe you've got one, because we saw back here, okay, that we can simply say the relationship between that is our Fn sine of theta to find Fr. So you can say Fr there from our vertical component understanding will be equal to Fn times what? The sine of theta. If it is the tangential force, Ft is going to be Fn cos of what? Cos of theta. So you can find Fn by dividing by cos of theta. Find Fn here by dividing by the sine of theta, depending with what you are given or what is it that you have on your information. So that one, guys, just play around with your mathematics. You see the advantage of mathematics. All right. Anyways, the normal force, tangential force, radial force are equal in magnitude on both gears, but they act in opposite what? Directions. They act in opposite directions. This is what you're seeing to say. For the driven gear, for the driver gear, will be having same thing. These two are identical. It is only direction to say we are now going to the left here. This one is facing to the right. Here it's going down. Here it is going up. But it will be the same. So when you're asked to calculate this, just use one. You use one part, all right? So I'm going to list formulas that you can actually use to calculate this, but you work with one, all right? You just work with one concept or just the formula. Okay, it is up to you, but listing this can help us to say, okay, this is what you're going to need on our calculations. So for the calculations, like I said, some calculations we are going to need them from our gear drives. There is no way. There is no way. There is no way. So I'm going to first list the ones that we need in this topic of our bearings, then those ones borrowed from what? From our gear drives. All right. So the major aspects, as we've got two things on our spur gears, we consider the driver, which is our pinion, and also the driven. So I'm just gonna separate them into two. That's our driver, which is the pinion. And just consider this one given as the pinion. That is the one. Remember I said it has lesser number of teeth compared to the what? To the driven gear, which is our gear wheel. So this one, that's our gear wheel. Or when they say the gear, that's we just consider the driven guys in your normal understanding. Don't panic. Just one and the same, like I'm saying, the information will be the same thing. So there we are going to calculate the torque for the pinion. So it follows that T pinion, which is the input. This one, it is the input. It is our input, this one. It is equivalent to the tangential force times the PCD of the pinion. So I'm just going to put small letters there over 2. All right, so that's in Newton meters. So there I'm just going to put the PCDs for the pinion in small letters. Remember, it's the smaller one. The driver is the smaller one compared to the driven. So here, that's for the output, which is our gear wheel. All right, is equal to Ft, which is our tangential, times the PCD of the gear wheel, which is I'm just going to put in upper caps. All right, so we consider our pitch center diameter. That is the major case there. So this is it in Newton meters. We also have the normal force. as we saw here, that if, let's say, we have got FT, because let's say we've got FR, it's up to you. If I have got FT here, let's say I've got FT, I can calculate FN. I can simply divide by the cos of theta, divide by the cos of theta. So that's going to cancel. So Fn is Ft over cos of theta. But remember, our theta is fixed. It does not change. It is always at what? At 20 degrees. So it follows that Ft is Fn is Ft over cos 20 degrees. So you can find Fn, the normal force. All right. So this was it, guys, on the torque. Like I say, this is the torque here, which is the same for the pinion, for the gear wheel. Like this is our in, this is our out. Okay, guys, I don't know how you can put it there, but anyway, that you understand. Then the normal force can also be determined if, let's say, I have got Ft, because from there we can simply make Ft the subject, guys. Let's just make Ft the subject, guys, so that next time when I'll be writing, I'll be just saying, okay, refer to the video that Ft, therefore, Ft will be equal to what? You multiply this by 2 to get rid of the denominator. So that's 2t over what? Over PCD. All right, so I'm just going to write it in short like this. To say, if let's say you want to calculate Ft, which is our tangential force, we are going to multiply to the torque in that case that you're given. Is it for the gear? Is it for the pinion? So that is what you're going to need. So if we say for the pinion, okay, let me just specifically write, because yeah, guys, some of us will be, we did not understand what happened there. All right, no problem. So let me just write as it is. So this is T for the pinion over PCD of what? Of the pinion. If we are referring to this side, the same thing. So it's going to be Ft is equal to 2 times, all right, 2 times the T for the what? For the gear wheel over what? Over the PCD for the what? For the gear wheel, like that. So it can make sense, so that we know, okay, I'm actually working with this. But guys, knowing one formula, you can make the subject of the formula. So this is what I'm trying to say. You have got your Ft, which is your tangential force. Now you can calculate the normal force from that formula that we manipulated here. Ft over cos theta. So it's going to be Ft over cos 20 degrees. So you can simply use that. So you see where it is coming from. All right. So that's Ft over cos 20. So it is the same. Remember, we said these are equal. So it is the same thing that you must obtain here. It is the same thing. Your Ft that you calculated there over cos of what? 20 degrees. It is the same answer that you must have. All right. So that is it for the normal force. Then we also consider another aspect, which is the radial. Remember, we also consider that we also have the radial force. So if we are to determine the radial force, it's gonna depend with what is it that you have. What is it that you have? In most cases, let's say you do not have Fn, because we can have it from Fn. Let's go back. Let's go back to our diagram. Okay. Here, I need to go back to the diagram. Here. If we are to consider the relationship here, Fr is written in terms of Fn. So let's say I have got Fn now. I can simply divide by the sine of what? The sine of theta, the sine of theta. Sorry, sorry guys. Why am I dividing? We are talking about Fr here. So already Fr is there here. Fr is already there. But I'm going to change to another one. So let's write the one that we have there. So the first one for our radial is simply from Fn as it is times the sine of what? Sine of theta, where our theta is 20 degrees. So it is the same thing even here, guys. Fn, a sine of what? Of theta, which is 20 degrees. But we might not have Fn for that moment. We might not have it. And there is Ft. What can we do? Because Ft, Fn, Fr, they are on the same diagram. Remember from that right angle triangle that we produced there. So let's relate these two, Ft and Fr. Ft and Fr. So what is the relationship between Ft and Fr? So we just assume as if Fn is not there. There are these two. What is the relationship between these two? Remember, according to theta, this is our opposite side, and this is the adjacent. Where opposite and adjacent is from our soccer tour, that's the ratio of what? Of a tan, opposite and adjacent. So it follows that the tan there is the one that we're going to work with. The tan of theta, which is the tan of 20 degrees, is equal to the opposite, our opposite, if is what? Which is Fr, over adjacent, which is our Ft, as we need Fr, because we have got Ft. Remember this one, let's say we've got it, and we need to find Fr. So what are we going to do? Simply cross multiply. So 1 times Fr, that's Fr, which is equal to Ft times the tan of what? 20 degrees. That's it. So this can be used when I have got the tangential force. I can calculate the radial force from there. So let's take that one also. So also we can say our Fr is equal to Ft times the tan. That one is what? Is the tan. The tan of 20 degrees. So that's the same thing here. Ft is equal to hey guys, where am I getting Ft now? Fr here is equal to Ft times the tan of what? 20 degrees. It's only that I have the diagram on the other page. All right, so this is it. We saw it from our trigonometrical ratios. Our trigonometrical ratios can tell us that. So with this understanding that we have now, we can actually answer any question pertaining this section of the forces on what? On spur gears. The forces on spur gears. Because as you can see, these are all the forces that we have. And depending with the connection there, we saw that there are also bearings. There are also bearings. Right? I think I removed it when I was talking. Okay, but if we consider here, where we talk of the reaction of those at the end. So it's another section that we must consider. But like I said, these calculations, they need you also to have the basics of what? The gear drives, as you can see here. Pitch center diameter. And you don't know about that. Pitch center diameter. So it means this will affect, it will affect your understanding or your calculations later on. Remember from your gear drives, here I'm just gonna take you back a little bit. All right, from gear drives. I'm just gonna take you a little bit to the gear drives. from the gear drives, we talked about simple and compound gears, where we refer to the spur gears. And this is exactly what we are talking about because we are referring to forces on what? Spur gears here. This is what we're talking about. Forces on spur gears in parallel. So from those gears, let's get back to the gear drives and treat them under gear drives. Remember those calculations of the module, this and that. So I'm just gonna list one or two things that we need there. There's the calculation of the module, which is M. The module actually is just the same value that will be given, whether as you're saying, I'm talking about the pinion, I'm talking about the gear wheel. It is the same thing, same number, same value. So that one, it is the pitch center diameter over T, which is the number of teeth. Remember, there's T for torque, there's T for the number of teeth. Here we're talking of number of teeth. Number of what? Of teeth. Then we've got the pitch center diameter. The pitch center diameter of gear, of the gear, all right, of gears. So that is what we have there. So meaning to say, where you are referring to the pinion, you use PCD. The number of teeth, you use small letter t. When you talk about what? The pinion, you use small letters there. All right? Capital letters, you're gonna use them for the gear wheel. So that's one thing for you to consider. Another thing for you to consider back when you are dealing with your gear drives. It is the velocity ratio. Yes, that one. I'm not gonna take everything, guys. Just go back and redo all those gear drives calculations. I'm not gonna take all. I'm just gonna take one or two that we need in this topic. All right. We have got the velocity ratio, which is our gear ratio. So you're going to consider the gear ratio. The gear ratio is equivalent to, it can be taken from the number of teeth. So you can consider the teeth on the gear, which is the gear wheel, and the teeth on the pinion. So the teeth on the pinion, just going to use small letter t if you're presenting your information or data. Then it can also be equated, all right? So here, let me specifically write that we are dealing with the number of teeth here because we can have the T for torque. Can have the gear over the pinion, but this T representing what? The torque. So that is how it can be like T out over T in, which is also equal to, we can consider the pitch center diameters, PCD over PCD. Remember, the bigger one when it's like this for the gear. All right. So that's for the pinion. This is also equal to the speed on pinion this time over the speed on the gear wheel. So the gear wheel ratio, the gear ratio can help us to find anything that is missing, especially here, the torque, especially the torque there, as we saw that the torque is needed. We need the torque here on these calculations. So especially on that one, you must be very careful because they can give you the number of teeth for both. You use that one to find the gear ratio, then you use it now to find the torque of one which is missing. They can give you both the pitch center diameters for both. You can use that one to find your gear ratio, then use it to find one of the missing on the torque there. They can give you both in terms of the speeds. Use it to find your gear ratio, then after that you can find what is missing on the torque because the torque is or will be needed on your calculations as we saw here. So that is what I can just bring from what you had before. This is what I'm just going to bring. And as a last segment, this one I'm not going to... Okay, let me go to the first page, the first party. This time, this part I'm not going to jewel much into it because you need to understand when we are doing questions. So make sure, guys, you join the membership so that you do not miss any of the questions that we are going to have later on. So here, I'm not going to draw much. I think I had an illustration before. We can have forces which are on a wheel and we can have a condition like, let's say they can say for a gear wheel, let's say a gear wheel is mounted on the shaft and the shaft support is supported by two ball bearings at the end. You have a shaft supported by two ball bearings at the end. But on it, there is a load which can be a gear wheel mounted there. I think I talked about this. So it will depend also with the information because the issue will be on the force that is going to result here. Normally, you take your reactions. As we do know, guys, the reactions will be facing up. So this is on the left. This is our right reaction. So what is happening here in between? You considered from the question. That is why I said I'm not going to dwell much because you need to know, is the normal force going up or is it going down? Okay. Yes, we do understand the weight. Whenever the weight is always facing down. Your total weight is going to be facing down. But the normal force, they can say it is going up. You must consider the way that they gave you, but in a normal consideration, when not given, you assume that the normal force is going down. You assume that it is going down. Unless stated otherwise, you use that condition. So we shall see that last aspect when covering questions. That is going to be our next section. Gonna go through some examples, questions to cover up or to cater these calculations that I mentioned here on our bearings and also the idea of our gear wheels. All right. So the last section that you're going to need as we are to cover this first part of loads acting on shafts. It is the loads on what? Helical gears. So helical gears, they look like ordinary spur gears, the ones that we have been talking about. They just look ordinary like that. But they're being machined from a stack of thin shim stock. Each one is rotated slightly with respect to its neighbors. When power is transmitted, both shafts are subjected to the thrust load on the what? On the shaft. So when the torque is transmitted, The tooth contact produces three forces. When the torque is transmitted, the tooth here, the tooth contact produces, it produces three forces. Namely, all right, we have got radial force, we have got the tangential force, and we have got the axial force. So those are the three forces that will be produced from that. So our next segment is looking into questions, examples, question papers, whatever that has the information that we've covered so far with those list of formulas that we have listed. So that is what we're going to do. So like I said, make sure that you join the membership so that you do not miss any of the calculations that you're going to have. And if you're part of membership, let me know the sections that need to be covered as we have illustrated now. This is part of membership that I'm doing right now. That is a request. So guys, membership, it is leave what you are doing. Can you do this for me? Leave what you are doing. Can you do this for me? Because I will be working on something and you'll be needing something. But that is it, guys. Let us join membership so that we don't miss anything from Mason African Motives till we meet again.